So in the last lesson, we discussed probability models for discrete random variables. And when we were describing those probability models in terms of measures of center and spread, we had to rely on the median and things like the range because we didn't have a means yet of calculating what the mean and the standard deviation of those discrete random variables were. So that's what we're going to be looking at in this lesson. How do we calculate the mean and the standard deviation for a discrete random variable? So we learned before that the mean x bar of a set of observations is just its average. When we're calculating the mean of a discrete random variable, we use the variable mu to represent that mean because it's all of the possible outcomes. And we use this little sub x to denote what it's the mean of. So we read this as the mean of x, the mean of the random variable x. And in this case, we're talking about a discrete random variable. So the mean of a discrete random variable x is also the average of all the possible values of that random variable x. But we have an important change that we have to make in order to take into account that not all of the outcomes are equally likely. The mean of any discrete random variable is a weighted average in which each of the outcomes is weighted by its probability. So suppose that we have a discrete random variable x with the probability distribution, where we have each of our outcomes and the probability of each of those outcomes. To find the mean or the expected value of that random variable x, we have to multiply each possible value by its probability, and then we add up all of the products. So in other words, the mean of the random variable x, which is also known as the expected value, and we'll come back to that idea in just a minute. To find that, we have to take each outcome, so x sub 1, and multiply it by the probability of that outcome, p sub 1, and then add them together. So then we have our next outcome, x sub 2, times its probability, p sub 2. And then we would have our next outcome, x sub 3, times its probability, p sub 3, and so on. And we would add each of those outcomes times the probability. In other words, we are summing, we are adding each outcome, x sub I, times the probability of that outcome, p sub I. And this is the way you'll see the formula written on your formula chart on the AP exam. So this just means to find the expected value or the mean of x, multiply each outcome times its probability, and then add them all together. Now we also call the mean the expected value because it's what we would expect typically. So just like before, the mean was kind of what was typical. The mean here is still what's typical. And so we can use it to calculate what we would expect to see on average based on a discrete random variable's probability distribution. So let's take that formula and apply it to an example. It says on an American roulette wheel, there are 38 slots numbered 1 through 36. Plus, there is a 0 and a double 0. Half of the slots between 1 and 36 are red, and the other half are black. Both the 0 and the double 0 slots are green. Suppose that a player places a simple $1 bet on red. If the ball lands on red, then the player gets the original dollar back, plus an additional $1 for winning the bet. But if the ball lands on a different colored slot, something other than red, then the player loses their dollar bet to the casino. We're going to use this to do two things. First, we're going to define a random variable, x, which is the net gain from a single player's, a single $1 bet on red, and we're going to show the probability distribution of that random variable. Then we'll use that information to calculate the player's average gain. So for part A, to find the probability distribution, what we need is to list all of the possible outcomes and their probabilities. So in this case, the value represents all of the outcomes of x, where x is the net gain from a single $1 bet. So when a player places a $1 bet, one of two things is going to happen. if it lands on a color other than red, they lose. So if they lose, their net gain would not actually be a gain. It would be a loss of $1. So we'd say negative $1 for their gain. But if they win, not only do they get the dollar that they bet back, but they get an additional dollar. So if they win, if it does land on red, then their net gain is $1. So they place the dollar bet, they either lose that dollar or they get it back plus a dollar, which means they gained a dollar. So you either lose the dollar or you gain the dollar. So your net gain is either -1 or +1. So now we need to calculate the probability of each of those possible outcomes. So let's start with the number of ways that the player could lose. It says that if they land on anything other than red, they lose. Well, we know that half of the 1 through 36 slots are black. So half of those 36 spots would be 18. So if they land on a black, they lose. If they land on any of those 18, they lose. But also, if they land on the 0 or the double 0, they lose because those are also not red. Those are green. So there are 38 possible outcomes. There are 38 slots that the player could land on. And of those 38, 20, this 18 that are black and the 2 that are green, would result in a loss, losing the dollar. Likewise, the probability of winning, again, there are 38 possible slots that we could land on. And in order to win, we would have to land on a red slot. And there are 18 different red slots, so the probability of landing on red and winning would be 18 out of 38. So this is our probability distribution. Now that we have that, we can use that to answer Part B. Part B wants to know, what is the player's average gain? Well, this is their net gain, either -1 or 0. The average of those will be the mean of X, because X represents their net gain. So we want to know, what is the average of their net gain? What is the mean of X? And to calculate the mean of X, we have to take each of the possible outcomes and multiply it times the probability of the outcome. So our first outcome is that we would lose a dollar. That would be our net gain, -1. And we multiply it times its probability, which is 20 out of 38. Then to that, we're going to add our next possible outcome, which is a net gain of $1, times its probability would be 18 out of 38. So if we multiply -1 times 20 out of 38, and we add +1 times 18 out of 38, what we end up with is 0.05. Oh, actually negative 0.05. And that's measured in dollars. So the player's average gain would actually be not a gain, but a loss of 5 cents on average is what we would expect. So what does this mean? Well, if someone played several games of roulette, we would call the mean amount that the person gained X bar. The mean in the previous example is a different quantity. It's the long run average gain that we would expect if someone played the roulette a very large number of times. So we're not saying that each player is going to leave the table and lose on average 5 cents. Their actual gain is going to depend on how long they play. But if they were to repeat this process over and over and over many times, then what we would expect on average is that that person would walk away losing about 5 cents. So for this reason, the mean of a random variable is also often referred to as its expected value. Just as probabilities describe the proportion of times an outcome occurs in many repetitions of chance process, the mean of a discrete random variable describes the long-run average of outcomes. So just like with probability, just because we know the theoretical probability, what should happen in theory, sometimes there's variation when we actually execute it. There's a difference between the empirical probability and the theoretical probability. The same thing is true for the mean. We won't always see exactly the expected value or the mean of x. But if we were to repeat this process many, many times, this is what we would expect. And that's why we refer to it as the expected value. So there's two ways of denoting the mean of a random variable x. We can use the notation mu of x, just like before, the mean of x, or we could write it as e of x, which is the expected value of x. In the roulette example, the mean and the expected value were a loss of 5 cents. This mean, with the mean as the measure of center for a discrete random variable, then we also want to adjust our measure of spread. So just like before when we were discussing measures of center and spread, we know that if we're using the mean as the measure of center, then the standard deviation is what we would use as our measure of spread to go with it. So just like before, we talked about the sample variance, S sub x squared, as the typical squared deviations from the mean. And then we could take the square root of that variance to get the sample standard deviation, S sub x. The definition of the variance of a random variable, sigma squared of x, is the average of the squared deviations, so each observation minus its mean squared of those values of the variable x from its mean mu of x. So as with the mean, each of the outcomes, sorry, there's a typo there, each outcome is weighted by its probability to take into account that the outcomes are not equally likely. To get the standard deviation of a random variable, we take the square root of its variance. So suppose that we have a random variable x with a mean mu of x. We calculate the variance of the random variable x, the variance of x, or sigma squared of x, by taking each of the outcomes, so starting with the first outcome, subtracting the mean, mu of x, and squaring it, just like we calculated the variance before. But now we have to weigh it. We have to multiply that times the probability of that outcome. And we would do that for each outcome. So then we take our next outcome, subtract the mean of x, square it, and multiply it times the probability of that outcome. And then we do that with the next one. So then we take the mean or the observation, the third observation or possibility, subtract the mean of x, square it, and multiply it times its probability, and so on. In other words, we have to take each observation, x sub I, subtract the mean of the random variable, square that variance, weigh it by multiplying it times the probability of each of the outcomes, and taking those for each observation and then adding them together. This gives us the variance, and just like before, once we know the variance, we can calculate the standard deviation simply by taking the square root. So then to find the variance, we take the square root of the standard deviation. We take the square root of the sum of each of the squared deviations times the probability of that outcome. The standard deviation of a random variable x is a measure of how much the values of the variable typically vary from the mean, just like before. The mean is what we would expect typically. The standard deviation is how far on average does each outcome typically fall from that mean. So let's see if we can take this and apply it to another example. We're going to go back to our APGAR scores from the previous lesson. So before we define the random variable x to be the APGAR score of a randomly selected baby, the table below gives the probability distribution for x once again. So this is the same probability distribution we were working with yesterday. So we're going to compute the mean of the random variable x and interpret its value in context. And then we're going to use that mean to compute and interpret the standard deviation of the random variable. So I would like for you guys to do the first part. We've already looked at an example of how we can calculate the mean. So apply that to find the mean value for x. So find the mean value for x. And then once you've calculated that mean value, come back and watch part 2, and we'll use that mean to compute the standard deviation.